galactic center. We live in a spiral arm, so looking 90 degrees from the center, we're looking down the spiral arm that way. That's here. If I look 90 degrees in the other direction, I'm looking at the spiral arm in the other direction. So it's evidence that we live in one of the spirals in the spiral arm that we can understand. If we subtract this away and blow the scale up by a factor of 100 again, we now see variation. The galaxy is saturated, but now we see variations at a part 100,000 level. You see a bunch of blue spots together, red spots together, red spots together, blue spots together. What you're seeing there are things that we're able to show, because we had multiple wavelengths, did not come from our galaxy, because we're looking away from the galaxy and it doesn't have the right dependence on wavelength, but didn't come from other galaxies, but came from the beginning of the universe itself. But these are variations at a part in 100,000. That may seem pretty noticeable, but if you've ever seen a billiard ball or a smoothly polished marble floor, that is much rougher than that. The early universe is nearly perfect, right? But it's those small seeds are going to be the things that are going to become the things that are interesting now, the galaxies. Right? So here's the history of where we are in these kind of observations. Penzias and Wilson made the original measurement. Had they measured the whole sky at 7 centimeters, with their big antenna, they would have seen a highly resolved galaxy along here, and then they would have seen a uniform glow that comes from the universe, but they didn't have the sensitivity to see any more than that. Then later with our airplane, we discovered the dipole. If you neglect that and just say it's due to our motion, then you see this map, and then there was a map experiment, renamed the WMAP experiment, and it has bigger antennas, so it has more resolution. You see the galaxy more resolved, but you see the cold regions together, and when you compare the large scales, they're almost exactly identical. They're within the noise of the observations, but you see more structure, and that more structure allows you to see more details about the embryonic universe. And so we are getting together a lot, and those structures are basically ultrasounds that tell us about how the beginnings are being made, but also how galaxies and so forth were formed. And so we're getting ready, we hope at the end of this month, to finally, they used to say 2008, but it got delayed, to launch the Planck Satellite. It'll be the third generation. So COBE had coarse resolution, WMAP had better resolution, but when you subtract away the signal from the galaxy, you have to smooth it some. Planck will have many more wavelengths and higher resolution, and the smudgy part means it will also have polarization information. There's lots of additional information we're going to get from it. So we're all excited about launching the next satellite. And we're in the middle of the great discovery area, just like the time of going around and discovering all the continents on the Earth. So here is, with the best estimate of the galaxy removed, what the COBE DMR is seeing. And if it flipped over, right, it would have made a map of the Earth that looks like that. It's hard to see Malaysia on here, right? You don't have the resolution, so you can't tell much about the early universe or the details. But here is now the WMAP measurement, as good as we have today. And here is a map of the Earth with the resolution that Planck will have. And now you can find Malaysia, you can find many other things. And here you can see interesting phenomena. It's very obvious when you start seeing the Mid-Atlantic Ridge, the shape here, the shape there, that the continents were once together, that there are nonlinear forces shaping the way the structure of the Earth looks like. But in the early universe, there are no nonlinear forces. We know there are no nonlinear forces down to a part in 10,000 level. We know that somewhere around the part in 100,000 level, there must begin to be nonlinear forces because gravity itself is nonlinear. The general relativity, the energy in the gravitational field makes gravitational effects. So we know there must begin to be nonlinear effects. So we're really trying to understand the forces that shape the structure of space-time. That's what we're trying to get. So now I have one more set of pictures I wanted to show you before I end up, and so we can ask questions. I'm running over a couple of minutes, but I'm sorry about it. So this is one of the 2 million or half-million galaxy maps that we have of the universe. So you just go out and take a picture like the Hubble picture, throw away the stars, estimate the distance of the galaxies, and plot them in 3 dimensions, and project it on here in 2 dimensions. So every dot on here is a galaxy. This is from the Sloan Digital Sky Survey, and as the Earth rotates and you take a series of pictures, you get a fan across the sky. So I can show you what the structure looks like, and what you'll first see is mostly the structure of the survey, where they looked and where they haven't. But if you look inside the survey, you'll begin to see the distribution of galaxies, and you will see that question about the great attractors is a much more complicated question than we even thought 20 years ago. So you see the fan shapes. It's not that the fans are only where we look. There's galaxies other places. But now you can see the galaxies are on a kind of a web, like a cobweb. It's a more complicated web than a cobweb. Oops. It's supposed to cycle, but it didn't. So let me show it to you again. You will also see a structure in here which we call the Great Wall. It's not just a string of galaxies. It's a great wall of galaxies. It has many millions of galaxies in it. So you see it there. Right? It's just a whole big sheet of galaxies across the sky. So we have questions. How likely is that to happen? How many of those should we see? You know, what should our simulations show? But you'll see there are voids, there are places where there are no galaxies, and then there's filaments and stuff. And this is sort of rough. There's another survey which we're going to fly through like we're on Star Trek. Except remember, the average distance between neighboring close by galaxies takes light 2 million years to go. So we're going to go warp factor about 1 million. So we're going by these galaxies really fast, right? Should take us 2 million years to go by, you know, from one galaxy to the next. But you will notice, not only do we know where 1 million galaxies are, we know what color many of them are. We know their shape. Some are spirals, some are evolved, some are ellipticals and involved. Some are you know, early galaxies. It'll swing around. You'll see the structure of the survey. This is really fast, right? We're going much faster than light. They would be distorted if you actually were looking this way. This is just the computer animation. But you could see what a Herculean task it is to map the galaxy, to map all the galaxies properly. But again, you can see the Great Wall. This is a different wedge in the sky. This thing sticks out across many, many places. And this is only the nearest million neighbors, right? And it's a sample of the sample, right? I mean, it should be many more than 1 million in our local neighborhood. But that's nothing. 1 million out of 100 billion, right? It's only a part in 100,000, right? It's a tiny sample. It's our neighborhood. It's like judging everybody in Malaysia by who's in the audience, right? And it's not a good sample. Okay, so what do we think? So now I'm going to show you a simulation. Oh, no, I'm sorry, I'm going to run over about 5 minutes here. But then I'll give you more. There'll be many more questions because I showed you this. So we're going to see on the large scale that the universe looks like this carpet. And now if you zoom in on the carpet, you see it's woven material. Here, when we zoom in, we're going to see something that looks very biological. It's going to be a random stochastic process that's only uniform on average. So I'm going to show you 2 simulations. There's 1 billion particles in this. So a gigaparsec is roughly 4 billion light years across. And we're zooming in, and now you see it's not regular. It's only uniform on average. It's not regular. There are all these filaments. It's like bubble web. It's like a spider web. It's 3-dimensional. They're going to zoom in on a place where many filaments come together. And in that will be a really unusual and interesting structure. This is an area where somewhere between 100,000 and 1 million galaxies are concentrated together. So we're zooming in, right? A parsec is 3.26 light years. Astronomers have really strange units. So that's 100 million light years. This is 50 million light years. And so we're zooming in, and eventually the distance between us and Andromeda will be about like that. So if you live down here, this would be downtown compared to, you know, living out in the suburbs. You would see galaxies everywhere in the sky. It would be bright, like living in the center of our galaxy. There'd be stars all around. Here, there'd be galaxies all around. So you get a very good idea of the structure when you get to be having the, you know, the plan view, like the architect's view of the universe. You get to see this structure. Now we're going to fly through the universe, and you can see how much harder it is to figure out the universe when you live in it. And even if you can fly at warp speed, ultra warp speed, now we're flying around. And one of the inventions that we had to make was, besides discovering the inflation, the fluctuations, we had to invent a whole new kind of matter called dark matter that doesn't interact with light. But in this picture, it's shown as white. And ordinary matter, the kind of stuff we're made out of, and plus the hydrogen and helium, it can be attracted into the structure formed by the dark matter. But because it can interact with light, it can dissipate energy and collapse and form stars. And so if you look in the cores of these dark matter halos, that's where you find the galaxies and the stars, and that's where you find the shining lights. So we're going to zoom in, and you'll see the structures. I apologize about the resolution on the screen. Okay, so we'll stop it here because I'm running over. Let me show you the simulation. So here's the cheating simulation. This is a small-scale version of the simulation. And you're going to start with an almost perfectly uniform universe, just exactly what we saw primordially. And we let the universe expand, but we keep the box the same size. We keep rescaling. Just because you want the map to be this big in your hand, you keep rescaling so the box stays the same size. And then you watch what happens. And what will happen is big clusters will start forming, and then they'll turn filaments, and then they'll slowly drift down the filaments. And so but this is only the dark matter in this simulation. It's only simple gravity. Oops. Sorry. What's happening on my screen and happening up there is not the same thing. So what you see happen is first you find the structures forming, and then they form filaments, and then you form this web, and then you have the structure on which you can then begin to put Christmas tree lights, which you call galaxies, or tracers of this structure. So that's really uniform, then little spots appear, and then those spots link up into filaments, and then you have this web, and then the ordinary matter collects on this web and lights up like Christmas tree lights. That's our picture of what happens in the universe. So we have a model of the universe which looks a little strange, right? We have the universe we believe coming from quantum fluctuations, expanding tremendously rapidly, beginning to slow down and cool down. And when it gets cool enough, then we can begin to let the matter flow. We can get a picture of that with the light. And then the first stars form, right? But they're forming on the back of the dark matter. And then the stars and galaxies evolve and come together and coalesce. So eventually, at about this point, we can make the solar system. We have enough material to make the solar system. We make the solar system, and we make planets, and life appears. But in the meantime, the universe has decided it's going to start expanding more rapidly again. So it was expanding more and more rapidly, then it started slowing down, and now it's starting to pick up speed again. This mysterious dark energy that's causing the universe to accelerate. But when you put this simple model in, and you do the calculations, compare, you can reproduce everything we see to the 1% level. So we know we're on the right track. The only question is what's causing all these things. So we have these interesting questions. So we've solved some problems. Now we have some exciting new problems for the next generation to work on. So the Big Bang is well established now. Nobel Prizes and princesses all around. I got to take, Crown Princess Victoria to dinner and Princess Madeline to dinner, so that wasn't so bad. And the dinner was really good. And there was good company. So we have this really interesting time now where we have a spectacular new universe with whole new sectors in it that we never imagined before. 20 years ago, we never would have guessed that they were here. We were just beginning to guess that we needed them. And the things that we know so well, they make up only 4% of